As mentioned previously, there's 3 conditions for a data race. We can eliminate the data race by eliminating any one of these conditions. And going in order, our first plan is going to be to eliminate data races by eliminating concurrent execution. Or we can restrict a data race by restricting one of these conditions. So we're going to restrict data races by restricting concurrent execution, and the example that I want to give is JavaScript. Now in JavaScript, this is true both in browsers and in like Node.js server environments, but we're going to use a browser for our example because that's easier. In JavaScript, the idea is we have no parallelism at all. There is logical concurrency, but never does code run on 2 CPU cores at the same time. Instead, we have functions running asynchronously, and each function or each task, I want to say, is going to run as an atomic unit. What the JavaScript runtime in a web browser actually does is it's going to sit in this thing that we call an event loop, where it's in this while loop. It's going to loop logically forever until the browser tab is closed. And when things happen, it's going to run either sort of task code, a function that's doing something, or it's going to run an event handler. And each of these tasks or event handlers runs synchronously and atomically, but because we don't know what order events are going to happen in, we don't necessarily know what order the event handlers are going to happen in, and so we get the logical concurrency that we need to deal with the sort of programs that JavaScript is designed to deal with. So let me go ahead and give an example of a JavaScript program. And the way I'm going to write a JavaScript program is I'm going to go ahead and open up an HTML file, and we're just going to type a web page. So web pages all start basically the same. Not teaching web development this semester, so I'm a little bit slower at typing web pages than I usually am. But this is the basic layout of a web page. We have the head, which has some metadata. We have the body, and almost everything goes in the body. Now, in our particular thing, 2 things are going to go in the body. We're going to have our content, which is just going to be a couple of paragraphs. One paragraph is just going to have a little bit of text, and then we're going to have 4 additional paragraphs, which are each going to have a button. So we're going to have a button named foo, we're going to have a button named bar, we're going to have a button named fib, and we're going to have a button named seek. Now, so far there's no code on this web page. We just have 5 paragraphs, 4 of them have buttons, and the buttons all have unique IDs. In order to make these buttons actually do anything, we need to add code, and that happens in a script tag. So for each browser tab, the browser is sitting there running a JavaScript runtime environment, and the JavaScript runtime environment is sitting there in the event loop, waiting for an event to happen or a task to be ready to run, and then it will run that task. Hopefully it will run it quickly. Most of the tasks that we have to deal with in a browser run pretty fast. They're not going to like visibly stop the web page from executing because they have to do things. But it's also important to make sure that they run reasonably fast, because otherwise the browser tab will freeze up. But when the web page is getting loaded, the browser goes through and looks for these script tags, and it runs them in order, and it runs them sort of logically synchronously. So for example, if we have a script tag up here, let's put it between the hello page and the buttons, and we put some code in here that will block. What that's going to do is it's going to mean that the web page or the web browser is actually going to render this paragraph, Then it's going to stop on this alert, and it won't be until we press the OK button that it will actually even continue rendering the page. It definitely won't run this script tag down here. So let me go ahead and... now, we know it's not going to run the script tag down here. I can put console.log hello in here. We can't actually see that. I could put... let's go ahead and grab that demo paragraph, and then we're going to say that the content of that is after the alert. So let's pull up a browser and go ahead and run this. Let me grab a browser. So we'll go ahead and say Firefox on that hello, and we can see exactly the behavior that we expected. The web page has the text of hello page up here at the top, and then we have, this is an alert, and that's blocked execution of the thing. As soon as we press OK, it's going to go ahead and run it renders the rest of the page, and it runs that second script tag, which is going to display the text after the alert. So let's head on back over to Emacs and make some more changes here. Let's get rid of this script tag, because that's sort of not the point. I just wanted to demonstrate that during page load, JavaScript will actually, it runs the stuff in order, and if at any point we block, we're just blocked. There is no sort of preemptive concurrency in the JavaScript runtime. The only reason we get this sort of logical concurrency behavior is that all of the code that runs very quickly, and that means that something else can get scheduled for the event loop. But if anything takes time or blocks, it'll stop everything. So now let's go ahead and add some event handlers for all of these buttons. So the way we add event handlers in JavaScript is as follows. We're going to say let foo button is going to be document get element by ID foo button. So now we have our button object assigned to this variable, and we can add event listener for the click event. And when we get that, we're going to call a function called clickFoo. Let's make a function clickFoo. Doesn't need any arguments. And then we will have this is what we're going to do when we click the foo button. And we don't want to do this. We want to instead say clicked foo. Let's add some more event handlers. So this is a simple event handler. When we click the button, that will cause that event to get scheduled, and then the next opportunity that the run loop has going through to handle an event, this event's probably next in the queue, and it will go ahead and execute this code in the event handler function. Let's make the one for bar a little bit more complicated. So I'm going to update, I bet I can just go ahead and change every instance of foo into bar. And now we have reasonable code here for bar, but I don't want to have it do quite the same thing. Instead, I want the click bar function to schedule an event for some time in the future. We have an API called setTimeout. It's going to take an anonymous function. Then after the anonymous function, we pass it a delay in milliseconds. And so this bar function, or the click bar function, is going to schedule an event for 2 seconds in the future. And when that event occurs, this event handler function, which doesn't have a name, but is still an event handler function, is going to get called, and we'll execute that code, and we'll see the result. And again, we have to set up the event handler in the same way that we did for foo. Two more cases I want to show. The next case is I want fib. So here, we're going to replace every instance of foo with fib. But instead of just saying that we're going to say click fib, we're actually going to calculate a Fibonacci number. We're going to calculate fib of 42. The reason we're calculating a Fibonacci number is because we can write it in an inefficient way, so it will take a significant amount of time to calculate. So here's Fibonacci. If x is less than 2, return 1, else return fib of x minus 1 plus fib of x minus 2. So calculating fib of 42 should take a little bit of time, and that will behave differently than in the bar case where we have a delayed event. When this fib function is executing, it will be executing. We can't do anything in parallel, so it's going to tie up the JavaScript runtime and prevent the event loop from doing any other tasks. Last example, I want to do a thing called seek. So we're going to replace every instance of fib in here with seek. And what we're going to do in the seek example is we're going to write a function. It's going to take an integer. When the seek function gets called, we're going to update the thing to say what number we're going to do, and then we're going to make this a recursive function. We're going to make this a recursive function in a sort of amusing way. Specifically, we're going to use Windows set timeout to make this be recursive, but with delayed recursive calls. So we're doing recursive scheduling of future events. So if seek is greater than 0, we're going to recursively call ourselves with k minus 1. So when we call the seek function, it's going to schedule a sequence of events that will happen until we run the number down to 0. And so unlike the bar case, where we schedule exactly one event, or the fib case, where while it's doing work, it's going to be tying up the event handler, this sequence function allows other things to be scheduled between these updates. So we'll see how that works out. So let's give this a try. And let's just make sure that we don't have any compilation errors in here. It's complaining about encoding, but the default behavior is fine. So I click foo, it says clicked foo, that's the behavior we expect. I click bar, there's a pause, it says clicked bar, that's the behavior I expect. If I click foo, bar, foo, we end up with clicked bar as the message because the event that causes the text to be updated to foo happened before the event that caused the text to be updated to bar, even though the button click for bar happened earlier. This is concurrency in action. This is the sort of concurrency that you can never avoid in a graphic user interface or a program with like network communication. And in a web page, we have both a graphic user interface and network communication. Now, if I click fib42, it's going to pause for a second. You can see that it's different here because when I click the fib42 button, the button stays down. So the button doesn't pop back up until the button click event is done firing. You can see that it takes about a second to fire that event. And so now if I click foo, fib42 bar foo, you can see it did all three things in an order. First, for like sort of a single frame flash, we saw fib42. Well, first it took about a second to calculate the value of fib42. And then we saw a single frame flash where we saw the number, but the foo click event had been scheduled. And so immediately it replaced it with that sort of backlogged event of foo. It couldn't run foo before it displayed the fib42 thing the way it did with bar, because while it's calculating fib42, it's busy doing that. And then we clicked bar after we clicked foo, so the bar click event happened after the foo click event, but that just scheduled the event that actually updated the text. And so a second after we saw foo, or 2 seconds after we saw foo, it updated to bar. Here's the seek thing isn't working. Let's go fix the bug. So I can click seek. We don't actually want seek42. What we want to do is just call seek with like 5, right? So let's go ahead and reload and then click seek, and it's going to not count down from 5 because I need to have the code be correct before it works. One more try. Seek. 4, 3, 2, 1, 0. And then it stops. So if I click seek, then foo, or bar, they get mixed together. If I click seek, then bar real quickly, we can get a case where it's going to show bar, and then we get a seek event again. So both seek and bar are nicely cooperative, sort of near instantaneous asynchronous events, and so they mix together in a perfectly reasonable way. In contrast, if I have seek running and then I click fib42, that stops the seek events from firing while it's calculating fib42. So importantly, we didn't miss any numbers. Whereas if we had parallelism, we would be able to do the seek events while the fib42 calculation was happening. So this is an important way to handle concurrency in a sort of modern environment. We can still have data races in this situation if we're not careful about taking advantage of the property that we get from this. The property that we get from the way this whole system works is that each one of these individual functions, like clickFib here, these execute atomically. So it's as if for the body of every function we held a lock. But the thing that makes it really easy to produce race conditions if you're not thinking carefully is that we can have multiple events in the same sort of text of the function. So here we have the seek functions event, but nested in it we have a separate function handler. And so these two, a separate event handler. And so these two events, the outer event and the inner event, don't execute together atomically. They each execute separately atomically. So it's as if, it's as if we took the lock at the beginning of each one of the functions and then gave it up at the end. It avoids data races in the same way that a lock would if we used it that way. But if that doesn't prevent the data race in the logic of our program, then the data race won't have been prevented. Usually that will prevent, like having a lock for every single function usually will prevent data races. So it's unlikely that you're going to sort of inadvertently get data races in this style of JavaScript, but you still conceptually could. All right, so that's plan A. Next video, we'll look at the next possible plan for avoiding data races in modern programming environments.